This lesson will focus on the comparison tests. So we've already developed a number of tests to decide about the convergence of series. We have P-series, we have harmonic series, we have geometric, and our integral test. So now a new test will be the comparison test. And the comparison test is a pretty simple test. It says, if I'm less than you and you converge, then I converge. Okay? So similarly, if I'm greater than you are and I know you diverge, then I must diverge as well. We will see that with an example here, 1 over 2 to the n plus 1. This makes you think about, of course, 1 over 2 to the n. Right? 1 over 2 to the n, we already know, hopefully, if you just think for a second, you should know the behavior of 1 over 2 to the n, whether or not it converges or diverges. But the question really is, what's the relationship between that and 1 over 2 to the n? Well, it's pretty simple. The denominator here is bigger, right? If the denominator here is bigger, bigger denominator means smaller number. Right? If that is the case, and we know, hopefully you already have that thought, this thing right here converges. If you're wondering why, think about it as 1/2 to the n. First term is 1, common ratio of 1/2, so we've got a geometric series. We know this thing converges, thus we know that one converges too. Okay, so the comparison test, if you assume you've got two separate series, A sub n's and B sub n's, and this says that they have positive terms, we're going to assume that both of them have positive terms. Now, if, and I'm going to leave out n equals 1 to infinity, if we know that B sub n converges, and, important fact, and you know that A sub n is less than or equal to B sub n, then you know that A sub n converges. Right? Now this, by the way, this statement is written in the textbook, it's written for all n, right? It says for all n values, it has to be true right here, that this has to be true for all n. So it means no matter where you are in the sequence of A sub n's and B sub n's, the A sub 5th term, A sub 5 must be smaller than or equal to B sub 5. Turns out that really doesn't matter, but it's extra safe to say that that's true for all n. Now, a similar statement would be to say if B sub n, again infinite sum, I'm just not writing it in, if the infinite sum is divergent, and that, then the A sub n is divergent as well. So think about what I could put in right there. It's basically just to say the opposite, which is what I said at the beginning. Probably 2 or 3 minutes ago I said, the first one, the way I phrased it was, if you're bigger than me and you converge, I converge. That's what this one says. This one says, if I'm bigger than you and you're divergent, then I'm divergent as well. Okay, so that's that. I think the idea here is really easy. It's like greater than, less than. The hard part, the crux, is how do you spot these things, and how do you look at something and say, what's the proper series for me to choose to compare it to? If somebody was to give you, oh, here's this series and here's this series, and you compared them, you might know which one's bigger, but the creativity here comes in when you look at it and say, well, should I choose this part of it to exploit or that part? So let's do a couple more examples. (5 over 2n squared plus 4n plus 3). Okay, So first thing is to decide if this thing is convergent or divergent. It's better, the sequence that this series is based on better go to 0. Obviously, 5 over very large number is going to go to 0. So that part's good, but remember, that was not enough to tell us that it converges. It's just enough to tell us that it diverges if this doesn't go to 0. But each of these terms, the sequence itself will go to 0. So now we need some further inspection. And think about when n is large, what really drives the behavior of this thing. And it's primarily this 2n squared here and the 5 there. There's nothing else going on in the numerator, so that's pretty much that. But the denominator is really dominated by the n squared. So really, the thing I'm thinking about is 5 over 2n squared. Now, what does this one have to do with 5 over 2n squared? Well, we just took away stuff from the denominator. So we made the denominator smaller. And when you make the denominator smaller, you make this one bigger. So now we have to analyze that. But again, that was probably the hard move. I don't think everybody would have looked at that and said, oh, I'm going to try this one. But now that we have that, it's pretty simple. This is really just n equals 1 to infinity, 5 over 2, and 1 over n squared. The 5 over 2 could even come out here if you wanted it to. That is a p-series. And it converges because p is 2, which is greater than 1. So this one converges. It's convergent. And if this is less than that, and that one converges, then this one converges as well. Okay. So let's do another example. Natural log of n over n. Okay. This one is definitely not going to immediately appear clear to everyone, but natural log of n over n. The first thing, like I said, always is to look at the sequence and decide whether or not that goes to 0. Okay? And that might not be super clear to you. Actually, we studied this one, I believe, with... I believe we did that question with L'Hopital's rule, but I'm not totally sure. One thing that I know about it, though, is that it's greater than 1 over n. Right? This, clearly, when n is big, is going to be bigger than that. Okay. If that's the case, then we look at this and we say, oh, that one diverges, and hopefully you know why that one diverges, because it is, hopefully you know, the harmonic series. And if this diverges and that one's bigger, then that one diverges as well. So now I've shown you the two sides of this comparison test. Okay. Now, one note I should make is this for all n that I talked about in here, that the sequence, the one sequence has to be smaller than the other sequence the whole time for all n. It's actually not, you don't need it to be true for all n. It can be true only for some n, because any finite number of terms is not going to drive the behavior of the infinite series. So in this one, this natural log of n over n, we don't have to verify that every one of these is greater than every one of these. Right? For example, the first term, natural log of 1 over 1, that's 0 over 1, which is 0, whereas the first term here will be 1 over 1. So we could go through term by term, but the major point here is it doesn't have to be true for all n. And again, that's because, let's just say your first couple terms, let's say you were operating on this one. And you had your initial thing that you're comparing to something bigger. If the first few terms of this one are bigger than the first few terms of this one, it's like, who really cares? Because these first few terms are a finite sum, and the rest of it is really what you care about, what happens out to infinity. So I just wanted to make a note here that it's not actually that big of a deal that it's for all, but it does have to eventually happen. It has to eventually happen, and forever after has to happen. So you should be able to specify some n value for which, okay, ever after this point, sequence A is less than or equal to sequence B, or the opposite for that. Okay, another one. And this one, we'll see, as always in math, we come up with a new idea, and then we pose a problem that sort of ruins it. Or at least ruins the ease of use. And this will do that. So 1 over 2 to the n minus 1. And hopefully immediately you're starting to think, okay, what am I going to compare this to? All right, I'm going to compare it to 1 over 2 to the n. So how does that compare to 1 over 2 to the n? Think about the denominator issue again, maybe even pause it, and you'll realize that that's the case. And it's like, okay, great, it's greater. I'm going to apply this bottom guy. It's going to be sweet. But this is convergent. That's convergent, right? This series. I should circle the whole thing. That whole thing is convergent. And you're like, well, so what? Well, there's an issue. This is greater than something that converges. Naturally, anything that diverges must be greater than something that converges. But the problem is, some things that converge are also greater than other things that converge. So this is actually not in our theorem. What our theorem says is if you have something that's bigger than something else, like that, it has to be divergent, right? If I am bigger than you and you are divergent, then I know I am divergent. If I'm bigger than you and you are convergent, I could be divergent or I could be slightly larger and convergent as well. So we're going to develop a new test, and that is the limit comparison test. Okay, the limit comparison test says, actually the same suppositions here, the sum, infinite sum of a sub n and b sub n have positive terms. So I'm doing a lot of abbreviating there. I didn't put my infinites and positive terms. What the limit comparison test really says is if you take the limit as n approaches infinity of the ratio of the sequences, not of the series, but just of their respective sequences, and that goes to C, in other words, converges to some C, and this thing is going to imply that either both a sub n and b sub n converge, or both diverge. I'm getting rid of our other comparison test here. So this again deals with limits of the respective sequences. So now let's get back to this question that pushed us off of our old limit comparison, or our old comparison test, and into this new one. If we let a sub n equal 1 over 2 to the n minus 1, and b sub n equal 1 over 2 to the n, limit as n approaches infinity of a sub n over b sub n will equal, well, that stuff. And that'll be 2 to the n over 2 to the n minus 1. And then you can divide through. I should still have my limit signs here, sorry. I'll put those in. Cheesy looking limit sign, nice work. And then divide through by 2 to the n, so we get that, which equals 1. And yes, so it equals 1, so now we have I was just checking to make sure. I was worried about an error in here. Not about, no, I think it's fine. So we know that it approaches some value, and in this case, the sum of 1 over 2 to the n minus 1 will converge. Okay, now let me just see if there's anything else. And if you're, the only thing I'm a little bit worried about is that you don't have the tie down, like this, what did this have to do with the other stuff? We created, we're basically doing a limit comparison test with 2 to the n and 2 to the n minus 1. We know 2 to the n converges, right? I know that one converges. So if that's the case, they either both converge or both diverge. And we know in this case they must both converge because we know one of them does. So yeah, that's that. And that's, first of all, the comparison test. If we said we have one that's less than the other, and the bigger one converges, then the smaller one must. And then we did a similar one for greater, and now we have the limit comparison test, which says they either both converge or both diverge, given that the ratio, their ratio's limit also goes to some constant value. So that is that. Thank you.